Welcome friends, this is Dr. Prashant Patil, Associate Professor, Department of Mathematics, Jain College of Engineering, Belagavi.
Welcome friends. In the last video I uploaded for the formation of partial differential equations. In forming the partial differential equation, there are two types we discussed. First type is by eliminating arbitrary constants from the given equation, and second one is by eliminating arbitrary functions. Now, before again starting with the formation of eliminating arbitrary constants, in this throughout this module we are using z as a function of f of xy, and we are using usual notations as dou z by dou x is equal to p or zx, dou z by dou y equal to q or zy, and second order partial derivatives dou square z by dou x square equal to r or zxx, dou square z by dou x dou y or dou square z by dou y dou x are one and the same. It is denoted by s, that is equal to zxy or zyx, and another one dou square z by dou y square equal to t, that is zyy. p, q, r, s and t we are using. Now some examples on forming the partial differential equation by eliminating arbitrary constants we'll discuss here. Let us form the partial differential equation PDE for the family of all spheres whose center is on z equal to 0 plane. That is important, z equal to 0 plane, and having the radius r equal to constants. Here we know that the equation of the sphere whose center at ABC and having radius r is given by x minus a the whole square plus y minus b the whole square plus z minus c the whole square equal to r square. Here ABC is the center anywhere in the sphere. Okay, but in this particular problem they given as center lies on the z plane, z equal to 0 plane. If z equal to 0 plane, on that plane the z coordinate c will be 0, the center c will be 0 for that. Therefore the center lies on the z plane, that is the z coordinate is 0, then a b comma 0 will become our center. Therefore equation of sphere is given by x minus a the whole square plus y minus b the whole square plus z square equal to r square. This is our equation of a sphere. Here a and b are arbitrary constants and r is our absolute constant. We may eliminate r square or it may remain in the equation itself. But to form the partial differential equation for this equation of sphere, let us differentiate partially with respect to x and y respectively. If we differentiate partially with respect to x, here x minus a the whole square, by using chain rule 2 times x minus a into differentiation of x minus a will become 1. Whereas differentiation of y minus b the whole square with respect to x will become 0, and differentiation of z square is 2z into dou z by dou x, that is equal to 0. Now simplifying, 2 cancels. If you shift to the other side, then 2 cancels. X minus a is equal to minus z into dou z by dou x is p. And in the second part, partial differentiation with respect to y will become x minus a the whole square will become 0. Differentiation of y minus b the whole square is 2 times y minus b into differentiation of y minus b will become 1 into z square differentiation is 2z into dou z by dou y. Here you are differentiating partial with respect to y. Simplifying this, shifting to the other side, y minus b equal to minus z into q. Then Here x minus a I know and y minus b I know. If you substitute in the given differential equation, given equation of sphere, we'll get z minus of z p minus of z into p the whole square minus z into q the whole square plus z square equal to r square. Then taking z square common, and due to square negative sign will eliminate, that is taking z square common, p square plus q square plus 1 equal to r square. This is your required PDE. Here r is absolute constant, that's why we are not eliminating this. In another example containing log, I will solve here. If z is equal to a into log of x square plus y square equal to b is the given equation. For this, what is our partial differential equation? Again, a and b are arbitrary constants. I have to eliminate a and b here. Differentiating partial with respect to x, dou z by dou x will become p, and a is constant. Differential of log of x square plus y square is a chain rule, considering this one as x 1 divided by x square plus y square, and differentiating x square plus y square with respect to x again. Differential of x square will become 2x. Differential of y square is 0, because we are differentiating partially with respect to x here, and differential of b is 0. Therefore, p equal to, I can write it as 2ax divided by x square plus y square. Like that, while differentiating partially with respect to p, with respect to y, dou z by dou y is written by q, and a into, again chain rule, 1 divided by x square plus y square into differential of x square plus y square with respect to y will become 0 plus 2y. Therefore, q is equal to 2ay divided by x square plus y square. Now I can solve for a here and substitute, but what happens? Again b will remain. That's why in forming the partial differential equation, after finding the partial derivatives, we can do any operation, addition, multiplication, or multiplying something to the one equation, and adding and subtracting can be done. But a and b should be eliminated, that is arbitrary constant should be eliminated. In this simple way, how to find the how to eliminate this a from this is dividing p by q. Then automatically our a will eliminate, p divided by q. P is 2ax divided by x square plus y square. Q will be reciprocated, x square plus y square divided by 2ay. 2a cancels, x square plus y square also cancels. Therefore, p by q is equal to x by y. Cross multiplying, py equal to qx, that is py minus qx equal to 0 is our required PDE. Okay. Now, similarly, two more examples I would like to explain here. Form the PDE from z is equal to log of b into y minus 1 divided by 1 minus x. Again here to eliminate a and b. To eliminate again constants, we are going for the partial differentiation. While taking the partial derivatives, you have to apply the chain rule here and then quotient rule and all those things. To avoid that, let us use the properties of log. We have the log properties as log of m into n is equal to log of m plus log n, and log of m divided by n is equal to log of m minus log n. Using those properties here, I can write the given expression as z is equal to a into log of b into y minus 1, m into n. I can write it as log b plus log of y minus 1 divided by 1 minus x is there. Therefore, m by n, log m, total m minus log n. Now it is very simple to differentiate. Therefore, differentiating one partially with respect to x, dou z by dou x will become p equal to a into log b constant 0. Differential of log y minus y also 0, because we are differentiating partially with respect to x. Therefore, differential of log of 1 minus x is 1 divided by 1 minus x into differential of 1 minus x will become 0, differential of minus x is minus 1. After simplifying, p is equal to a minus of minus plus a divided by 1 minus x. Similarly, partial differential with respect to y, q is equal to a into 0, 1 divided by y minus 1 into differential of y minus 1 will become 1 minus 0. This is totally 0. Log of 1 minus x differential is 0. Q is equal to a divided by 1 minus. Again, I have to eliminate a here. In spite of substituting in the given equation, I will divide p divided by q. P divided by q, that is a divided by 1 minus x into reciprocal of the q, y minus 1 divided by a cancels. Therefore, y minus 1 divided by 1 minus x. Cross multiplying 1 minus x into p equal to y minus 1 into q, or simplified form equal to, this is our required PDE. Up to these, whatever the examples were solved are containing only p and q, that is first order partial differential equations. If the differential equation is containing number of arbitrary constants more than the number of independent variables, then the differential equation is of a second order. In the previous examples, all our arbitrary constants are same as a number of independent variables. X and y are independent variables 2, and a and b are also 2. That's why we are getting first order. But in the next example, forming the PDE by eliminating arbitrary constants a, b, c. In this particular example, a, b, c are arbitrary constants, but whereas x and y are only two independent variables. Therefore, here the differential equation we are going to get is of order 2. Okay. Now, differentiating one partially with respect to x, I am getting 2x divided by a square, y square divided by b square is constant now because differentiating with respect to x 0, and throughout this model we are considering z as a function of x and y. Therefore, z square differentiation is 2z divided by c square into dou z by dou x, chain rule, equal to 0. Simplifying this, 2x divided by a square is equal to minus 2z divided by c square into dou z by dou x. 2 cancels, and rearranging this required terms, x into 1 divided by z into dou z by dou x equal to minus a square by c square. Like that, if you differentiate partially with respect to y, you will get 0, 2y divided by b square plus 2z by c square into dou z by dou y equal to 0. Simplifying this, 2 cancels, y into 1 by z dou z by dou y equal to minus b square. If you want to eliminate this a and z from the both equations, it is not possible. Only c square I can eliminate, but not the a square and b square. That's why you have to differentiate this one again with respect to x. While differentiating again with respect to x, I'll consider the three terms. X as one term, 1 by z as one term, dou z by dou x as one term. Then again I will apply the product rule for this. X into 1 by z as it is, partial differential of dou z by dou x with respect to x, dou z by dou x into dou z by dou x, plus x into dou z by dou x as it is, differential of 1 by z with respect to x will become minus 1 by z square into dou z by dou x, chain rule again here, and 1 by z, next third term will become 1 by z into dou z by dou x as it is, differential of x will become 1, which is equal to 0. Simplifying this, x divided by z into dou square z by dou x square minus x divided by z square, x into minus 1 by z square into dou z by dou x the whole square plus 1 by z into dou z by dou x equal to 0. And this is our required PDE. In this form also you can keep, or to eliminate this z multiplying throughout by z square, I will get z cancels, 1 z x, dou square z by dou x square is nothing but r, dou square z by dou x square is nothing but your r, minus Z square cancels, x into dou z by dou x is equal to p, and 1 by z will become 1 z will cancel, z into p. This is a required partial differential equation. Same thing, you can differentiate second part also with respect to again y. You are going to get the partial differential equation the same form. This is of a second order because r is present here. Thank you.